So in this video we're gonna start chapter number 9, which is acid and base, pH and buffers. So in this PowerPoint on this chapter we're gonna talk about several things. The first we're gonna start with the definition of acid and base. What are acid and what are base? We're gonna learn about this thing. Then we're gonna talk about the pH, the acidity of the solution, and then we're gonna talk about the reaction between acid and base, which is we call as neutralization reaction. And at the last we're gonna talk about a special solution which normally called as buffer, which resists any change in the pH. So we're gonna talk about this thing. So let's get started with our chapter. And then let's get started with our first topic for this chapter, which is acid and base. So you might have already heard of this term before in regular life or real life, that many of the food items that we normally eat or use have some acid in there. For example, lemons contain an acid in there, right? That's why the taste of that lemon is a little bit sour. So we're gonna start with the definition of acid and base, and then try to figure it out how we can determine whether the particular chemical or an acid or the compound can behave an acid or a base. So let's go to the next. So now let's start with the definition of acid and base. The first definition of acid and base was given by a scientist called Arrhenius. And according to this scientist or chemist, the definition of acid is whenever you dissolve an acid in water, they always produce a hydronium ion, H3O+. So that means if you have an acid, if you dissolve that acid in water, you will always get an hydronium ion. Or you can say those chemical or compound that can give out the proton, we call that as acid too. For example, hydrochloric acid, right? So when you dissolve this in water, it's gonna produce H+ ion and chloride ion, Cl. So that means hydrochloric acid is an acid because it can produce or give out the proton. This H+ ion we call as proton, right? So if this proton, so if I dissolve this hydrochloric acid in water, what we have in water, we have H2O, and this H2O we have a lone pair. And because of the presence of lone pair on water, this proton can bind with the oxygen to produce this H3O+, which we call as hydronium ion. So both the definition are right. So acid are those compound or chemical that can produce a proton when dissolved in water or a hydronium ion, right? Both are same thing. So let's take an example over here again. So this is hydrochloric acid. You have water in here, and then what's gonna happen during the reaction? The hydrogen from the hydrochloric acid is gonna go on the oxygen, right? So basically hydrogen is your proton, H+. And once we're done, you're gonna get the H3+ ion, which we call as hydronium ion, and then you're gonna get Cl-, right? So what's happening over here, the bond that you have between H and Cl, and then we know that to make a single bond we need 2 electrons, right? So the electron is gonna take up by the chlorine, and then hydrogen doesn't have any more electron in there, that's why it get a positive charge, and then the chlorine will get 8 electron in its outermost orbit, that's why we have a negative charge. So this is the basic concept for acid definition for given out by the Arrhenius, right? Let's take one more example, HBr. If you have hydrobromic acid, is it acid or base? Let's figure it out. If you put this hydrobromic acid in water, so what's gonna happen? Again, the hydrogen from the hydrobromic acid is gonna come and then bind with the oxygen and produce H3O+ ion, and then the bromide will get a negative charge, -1 charge. So that means hydrobromic acid is an acid. Why? Because in water is gonna produce, or hydrobromic acid is producing H3O+ ion, and this is the definition given by the Arrhenius. So make sure you remember the definition, right, of acid. So now let's talk about what are the base according to the same chemist Arrhenius. Which compound can behave as a base? So according to the Arrhenius, bases are those compound or chemical that can produce a hydroxide ion in water. So if any compound or chemical can produce this hydroxide product when it dissolve in water, when it react with water, that means that compound is base. For example, sodium hydroxide, NaOH. When it dissolve in water, what's going to happen? The OH component is going to get separated from Na. Right, so what you're seeing over here, NaOH is a solid in state before it react with water. Once you dissolve that solid sodium hydroxide in water, it's gonna get dissolved, and now it can separate it into an ionic form, Na plus and OH negative ion, and then if you see the state is in aqueous form. So that means this compound is giving out the hydroxide ion when dissolved in water, right? So that means this is a base. For example, one more compound, potassium hydroxide, KOH. When you dissolve in water, right, if this is in solid, what's going to happen? You will get ion K plus and OH negative ion, and the state will be aqueous, AQ. And then we can say potassium hydroxide is a base. Why? Because after dissolving in water, it's giving out the hydroxide ion as a product, right? So yeah, so you can say any compound that has the OH ion or OH ion already present in the compound, and then it's gonna give you the hydroxide ion after dissolving in the water, you can say those compound as a base according to Arrhenius. So now let's go to the next slide, and we're gonna see what kind of element from the periodic table can form this kind of base. So now let's talk about what are the different ionic compound we have in group 1A and group 2A which can behave as a base, right? So as we know, group 1A, we also call that group 1A element as alkali metal, and then group 2A we call as alkaline earth metal. Right, so the element that belongs to group 1A and group 2A, if they form an ionic compound with a hydroxide ion, they can behave as a base. For example, sodium hydroxide. Sodium belongs to the group 1A. If it binds with the hydroxide ion to make an ionic compound, and they can behave as a base, because if you dissolve the sodium hydroxide, which is in solid form, and if you dissolve in water, you're gonna get two ions, sodium ion and hydroxide ion. And because you are producing hydroxide ion while dissolving in water, sodium hydroxide is a base. Same thing with potassium hydroxide. If you dissolve this in water, you're gonna get K plus and OH negative ion. Ions get separated, right? So it's also producing the OH negative ion. So potassium hydroxide is a base. And what's the characteristic of the element that can make this kind of ionic compound with hydroxide ion and belongs to group 1A? They are mostly soluble in water, and they are also a strong electrolyte, and we already talked about the electrolyte in the solution chapter, previous chapter. So electrolytes are those solutions that can conduct electricity, and then which kind of solution can conduct electricity? Those solutions that have a freely available ions, right? And then the fourth one is dissolve entirely to produce an ion in water, because this is a strong electrolyte, and strong electrolyte means whatever the ions you have in that particular ionic compound, everything is going to get separated in a product form, right? So everything and every solid ionic compound is going to convert into a ionic form, whereas in group 2 element can still form a base with a hydroxide ion like calcium hydroxide and magnesium hydroxide, and then once they get dissolved in water, they're gonna produce, for example, from magnesium hydroxide you're gonna get magnesium and hydroxide ion. But what's the difference? They are slightly soluble in water compared to the group 1 element ionic compound, and they are also a weak electrolyte, means the ionic compound is not gonna convert completely into the ions when you dissolve in water. That's why it's a weak electrolyte. And because it doesn't convert entirely into an ionic form, that's why you have very slightly produced ions in the water, right? That's why you have very less amount of ions present in water if you have any base from the group 2 elements. So make sure you understand this concept, and then can differentiate between the solubility and then the electrolyte solution between the two groups. So now let's try to do some problem based on the concept that we just understood from the previous slides. So the first problem says HF, HCl, HBr and HI all are acid. What common product do they all produce in water? So we know already by the Arrhenius concept that if any compound behave an acid, and if you dissolve those acid compound in water, they're gonna produce always the hydronium ion H3O+. So we'll take an example of HF, react with water. Hydrofluoric acid is a weak acid, so we're gonna talk about this thing later on, but the concept is gonna produce H3O+ and fluoride ion. So this is the reaction. Now let's go to the second problem that says which of the following ionic compound is a base. So you have to figure it out of the 4 compound that is given. You have to figure it out which one is your ionic compound is a base. So let's start with each of them separately. With the first one, barium hydroxide. How would I know this is a base? So this is a base because it has hydroxide ion. When you dissolve this in water, you're gonna get barium +2 and hydroxide ion. And because you are producing hydroxide ion when you dissolve in water, this is a base. Second one is sodium bromide. It doesn't have any hydroxide ion in the compound, so when you dissolve this thing in water, you are not going to produce any hydroxide ion, so this is not a base. For the C, lithium hydroxide, as we know, this lithium belongs to the first group, alkali metal, and it also has the hydroxide present, so this is an ionic compound. When you dissolve in water, you're gonna get lithium aqueous plus hydroxide ion aqueous, AQ, right? And then if this is a solid, lithium hydroxide, so this is a base. What about the D, calcium bromide? If you dissolve in water, it won't give you any hydroxide, it will give you calcium ion and bromide ion, but it doesn't give you any hydroxide ion, so we cannot say this is a base. So out of the 4, barium hydroxide and lithium hydroxide, these are the only 2 bases present, right? So this is how you can explain and figure it out whichever the compound can behave as a base or acid, right? So now let's go to the next slide and then see if there is any more definition from other scientists already given about the acid and base. So now we're going to talk about the definition of acid and base given out by the second scientist, which we name as Bronsted and Lowry, and they gave us a theory of acid and base, and then we're going to talk about this thing. But before we go further, let me ask you this thing: why these scientists predicted a new theory even though we already have the Arrhenius theory in hand? So if I ask you this thing, ammonia NH3 is a base or acid, how would I know according to the Arrhenius? Because it does not have any hydroxide ion, right? Can we see any hydroxide in here? No. So if you dissolve this thing in water, this ammonia won't give you any hydroxide ion, right? And then according to the Arrhenius, we cannot say this is a base, but actually ammonia is a base. So we need to modify the Arrhenius concept a little bit. That's what the Bronsted and Lowry, the 2 scientists, did. They updated the Arrhenius concept a little bit and modify, right, by putting a more general definition of acid and base that we're gonna learn right now. So according to this Bronsted and Lowry theory of acid and base, acids are those compounds that can produce proton, right, which can donate proton. And according to them, base is those compound or a molecule which can accept a proton. So we can say acid is a proton donor and base is a proton acceptor. They can accept the proton, right? So now let's try to get this information and apply this concept with ammonia and figure it out whether this Bronsted and Lowry theory can be applied on ammonia, and figure it out whether ammonia is a base or an acid. So let's take an example. You have ammonia, NH3. If you put in water, you're gonna get NH4 plus and you're gonna get OH negative hydroxide ion. So now let's try to figure it out why ammonia is a base in this reaction. Acid is water. So let's try to understand. So what's happening in this reaction? So to understand this reaction, you have to look on the product side, which is on this side. So we can easily see ammonia is getting converted into NH4 plus, and then how would the ammonia is going to get the extra hydrogen, because in the beginning you have NH3, now you have NH4. So there is nothing else beside water who can donate a proton to the ammonia. There is no one else. So in this reaction, the proton, which is H plus ion, is given out by water, and once the proton is gone from water, what's left? Just OH negative ion, because water is what? Water is H and OH, right? So H is gone, the leftover is OH. Right? So let's understand the concept. So in this reaction, water is giving out the proton to the ammonia. So ammonia is what? Is your proton acceptor, because after accepting the proton, ammonia is converting into NH4 plus. So that's why ammonia is a base according to this definition. Which one is an acid? Water is your acid. Why? Because water is the molecule that is giving out the proton, which is being accepted by the ammonia, right? So that's why water is an acid. Now the second question is, why ammonia is getting a positive 1 charge? Why is not just NH4? Because proton has a positive 1 charge and ammonia is a neutral. So whenever the proton is going to attach with the ammonia, is bringing up extra +1 charge to the neutral molecule. That's why you have a net charge of +1 right now. And why OH is getting a -1 charge? Because OH is getting formed from the water, and in water the net charge is 0. But if you taken out the positive charge from the water in the form of proton, then you have to have a hydroxide ion to neutralize that positive charge, right? So this is how the reaction work, or this is how you can get an idea to figure it out which one is acid, which one is base, according to Bronsted and Lowry. So let's take one more example on the next slide, and then try to understand a little bit more about this concept. So now let the reaction, the example that is given over here between hydrochloric acid and water, and we're going to figure it out whether which one is acid, which one is base. Even though this is already saying hydrochloric acid is an acid, what is a base, but we're going to figure it out how according to the Bronsted and Lowry concept. So if you can see, HCl react with water, and what product you're gonna get? You're gonna get hydronium ion, which is H3O plus, and you're gonna get chloride ion, Cl negative. So what happened in this reaction? So water is going to convert into a H3O plus. So from where the extra proton comes or came? So it came from the hydrochloric acid proton, right? So the proton is going to attach, hydrochloric acid is going to give out the proton, and then the electron that is being shared between the hydrogen and chlorine is going to go on chlorine. That's why chlorine has an extra electron, which is 8 electron now, and with a -1 charge, right? Now proton doesn't have an electron, and how many electron hydrogen need to get stable? 2 electron, and oxygen has a lone pair of electron, so it can give out the 2 electron to the proton to complete its octet. That's why proton can attach with the oxygen, and now you have a hydronium ion with a positive charge on oxygen, because this is the one that donated the electron, right? So according to the Bronsted and Lowry, HCl is your acid because this is a proton donor in this reaction, and water is a base because this is a proton acceptor. Right? So this is how it works, right? Let's try to go to the next slide, and then we'll see the same reaction that I already explained to you about the ammonia, but let's do it. Let's see it and go on the next slide. So on this slide we have the ammonia and water reaction that we already done on the first slide when we talk about the Bronsted and Lowry, but let's do it one more time on this slide too. Ammonia is NH3, water is here. So in this case, during this reaction you made two product, hydroxide ion and ammonium ion. So if you see on the product side, ammonia has an extra hydrogen, and from where this extra hydrogen came? It came from the water, and water donated the proton H+ ion that is being received by the ammonia. Why? Because ammonia has a lone pair of electron, and ammonia say, okay, I have 2 electron, I can give it out to the proton and to complete its octet. So proton can come and then attach to the ammonium ion or ammonia to make it ammonium ion. So in this case, water is acting as a proton donor. So that's why water is a base in this case, or acid in this case, and whereas ammonia is your proton acceptor. It's accepting the proton, so that's why it's a base. So this is how you can verify acid or base in any chemical reaction, if you can see which one is giving out the proton and which one is receiving the proton. But the important thing, one more important thing between the two reactions that we did in the previous reaction, what we did, we reacted HCl with water to get hydronium ion and chloride ion that we did in the previous slide. In that slide, water is acting as a base, if you remember, and HCl is acting as a acid. But now in this reaction with ammonia, water is acting as a acid. So how is it possible? Then in the previous reaction, water is acting as a base. In this reaction, water is acting as an acid. So we're gonna talk about this concept where one molecule can act as an acid as well as base depending on where they're being used in the reaction, right? So let's go to the next slide, and then we're going to talk about this concept. So now let's talk about the concept that we just discussed on the previous slide about water. So in one of the reaction, water is acting as an acid. In the second reaction, water is acting as a base. So we have a special definition for the compound or chemical that have the ability to behave as acid as well as base depending on the reaction that they are being used. So we call those kind of compound or a chemical as amphoteric compound. So what is amphoteric? Any substance or molecule that can act as an acid as well as a base, we call as amphoteric. So water is an example of amphoteric substance. With HCl, it can act as a base. With ammonia, this is acting as an acid, right? So what is an amphoteric substance? Now we're gonna learn about how would you know which proton or which hydrogen can be donated during the reaction, right? So only certain hydrogen atom in the molecule or a compound can be donated, and these proton or hydrogen are usually indicated at the beginning of the formula. For example, hydrochloric acid, the hydrogen that is placed at the beginning of this compound this is the hydrogen that is being donated to the base. For example, acetic acid, this is the hydrogen which is going to be donated by acetic acid, and this molecule can behave as an acid. So let's take an example over here again of HCl. HCl plus water gives you H3O plus and chloride ion, Cl negative. So in this case, this is acid, this is behaving as a base, right? So this is your H3O plus, right? So we have a special term too on the product side. So if you see carefully over here, hydrochloric acid react with water, giving you the hydronium ion, which is this, right? And then HCl by itself is going to convert it into chloride ion. So we have a special definition. So according to that definition, the molecule that is acting as an acid, after it done behaving an acid, it's converting, or is already converted into a conjugate base, right? So chloride ion came from the HCl, and HCl is what? Acid. But after the reaction is done, the Cl part from the acid is going to convert into Cl negative, and this Cl negative is acting as a conjugate base. Why? Because now chloride ion is ready to take the proton from somebody else to convert back into HCl, right? That's the definition of the base who can accept the proton. Whereas the base, the molecule that is acting as a base in the reaction, once the reaction is done, that compound now behave as a conjugate acid. Why hydronium ion is your conjugate acid? The term acid normally indicate you have an extra hydrogen that you can donate. So now water is converting into H3O plus ion, so you have an extra hydrogen that came from the hydrochloric acid, right? Now the hydronium ion can donate the same hydrogen that it took from the hydrochloric acid to somebody else, so this can act as an acid. So just remember, in any chemical reaction, according to the Bronsted and Lowry, the compound that is behaving in an acid is going to convert into a conjugate base, and the base is going to convert into a conjugate acid by taking up the proton from somebody else. And that's how you can make an acid conjugate base pair, right? A base conjugate acid pair. So let's take some more example, and then we're going to figure it out the concept of this. So let's try to understand more about the conjugate acid and conjugate base. So let's take the same example of ammonia NH3 react with water, giving you ammonium ion plus hydroxide ion. So in this reaction, we already know about this thing. This is your base, this is your acid, water. Now in the product side, what we got? The ammonia is getting converted into ammonium ion. So that means now ammonia has an extra hydrogen that it took from the water. So that same hydrogen, ammonium ion, this is your ammonium ion. Right. So the ammonium has an extra hydrogen that it took from the water during the reaction. Now the same hydrogen can be donated by the ammonium ion to somebody else. So it has an extra hydrogen. So that's why it can act as an acid, and we have a special name called conjugate acid. Whereas water converted into a hydroxide ion. So that means it behaves as an acid, but after the reaction, after it donated the proton to the ammonia, it left with OH negative ion. So it can take an hydrogen from somebody else to convert back into water. So according to the concept of Bronsted and Lowry, OH negative ion can act as a conjugate base because it has the tendency or the ability to take the proton. and then whoever take the proton, base. Ammonium ion can donate the extra proton that it took it from water, can act as a conjugate acid. So you have a pair, that is, I can say ammonia and NH4 plus from this reaction. This is an base, this is conjugate acid Ca, and I can say this thing to water converting into a hydroxide ion during this reaction. It was behaving an acid, but after the reaction it can behave as a conjugate base Cb, right? This is your Ca, right? So we have a pair. So the molecule that can act as a base is going to convert into a conjugate acid. So this is a pair of base as well as conjugate acid for ammonium and ammonia, and then for water and hydroxide ion, this is a pair of acid and its conjugate base. So what's the special thing you are seeing over here? Let's start with ammonia. So the ammonia molecule which act as a base, and then during the reaction if it converted into a conjugate acid, it has an extra hydrogen. So whenever any molecule acting as a conjugate acid, you always put an extra hydrogen to the original molecule. In this case is ammonia, right? So conjugate acid always has extra hydrogen or extra proton. That's why it's an acid, right, from the parent molecule. Whereas a conjugate base always have less hydrogen or less proton compared to their parent molecule, right? So water has 2 hydrogen, hydroxide has 1, and because it can take one more, that's why it acts as a base, so that's why it has less hydrogen than the parent molecule. Similarly ammonium ion has 1 extra hydrogen or proton compared to its parent molecule NH3. That's why it's acting as an acid. So if I ask you write the conjugate acid for any molecule, you always add an hydrogen to the parent molecule. Or if I ask you write the conjugate base for a parent molecule, you can take out the hydrogen, one of the hydrogen from the parent molecule, and rest of the compound will be your conjugate base. So let's try to understand the same concept on the next slide. So let me give you an example. If we have hydrochloric acid, and if I ask you write the conjugate base for hydrochloric acid, so this is our parent molecule, and then to make a conjugate base, the time I say is a base, that means it has 1 less hydrogen than the parent molecule. So I can say Cl negative, because hydrochloric acid, if you took out the proton H plus ion, then you left with negative ion, right? Because when they combine again together, they have a neutral molecule. If I give you one more example of HPO4 2 negative, right, or H2PO4 negative, let's talk about this one. If I say write conjugate acid for this compound, so the conjugate acid, the time I say acid, you should put 1 extra hydrogen to the parent molecule. So the formula will be H3PO4. I provided 1 extra hydrogen, 2 to 3, and the time I'm providing an extra proton, then this negative charge is going to neutralize with an extra proton that I'm providing this molecule with, so there won't be any charge. So this is H3PO4 without any charge. But if I say write the conjugate base, the time I say base, take out an extra hydrogen or proton from the molecule. So we have H2PO4, we are going to take 1 proton away from this molecule. So our product will be HPO4 negative 2. Why we are having an extra negative than the parent molecule? Because when you took out the proton, you are taking out an extra positive charge, and to neutralize that extra positive charge, you have to have an extra negative 1 charge too, right? And then this is your conjugate base, HPO4 -2. So make sure if you are taking out a proton, you are giving out the same number of negative charge to the molecule. If the molecule is neutral, then the final product will be -1 charge. So you have to just decide by yourself how many proton you are taking, if you're taking from the neutral molecule or you're taking from the ionic molecule. Right. So let me give you one more example over here. If you have HSO4 -1, what's the conjugate base for this compound? What's the conjugate acid? So for conjugate acid, put one hydrogen or proton to this molecule, to the parent molecule. So you're gonna have H2SO4. The time I say base, take out the proton from the original molecule. So we have just with SO4 -2, because we are taking a proton, that's why the charge will increase by 1, -2. So this is how you have to decide which charge you're gonna get and where you need to put the proton and where you need to take out the proton. And yeah, so this is how you can make conjugate acid and base. So let's go to the next slide and then see one more example over here. If I give you this HCO3 -, if I say write the conjugate acid Ca, what should be the conjugate acid? You put an extra proton to there, right? For acid you put an extra proton, so you're gonna get H2CO3, and then you won't have any charge anymore because you are providing a H plus, so it will neutralize. If I say write conjugate base, so in conjugate base you're gonna take out the proton from the original molecule. So from the HCO3 if I take out one of the proton, the charge will get increased by -1, so you will get CO3 -2 charge on the top. So make sure you practice to make several example how to make a conjugate acid or a conjugate base. Now let's try to do this problem from all the concept that we just learned about the conjugate acid and base pair. So the first example says sulfuric acid H2SO4 react with water, gives you a hydronium ion and HSO4 -. So you have to tell what are the pairs. So if I say H2SO4 is converting into HSO4 -, so that means an H3O is converting into H3O plus. So that means water is getting an extra hydrogen. So this is acting as a base B, sulfuric acid acting as an acid A, and then H3O plus is your conjugate acid, and then HSO4 - is your conjugate base. So I can say H2SO4 is converting into HSO4 during the reaction, so acid is converting into conjugate base, and H2O converting into H3O plus, I can say base is converting into conjugate acid. So we have these pairs: acid conjugate base pair, acid conjugate acid base pair. Now, let's do the second one, where you have HCO3 react with water, gives you hydroxide ion and carbonic acid HCO3. So in this case, what we have over here, HCO3 is converting into H2CO3. That means this HCO3 is getting one extra hydrogen from somebody else, and who's going to provide that hydrogen or proton is water. So water is acting as an acid and this is acting as a base. So in water, after donating the proton, it is itself is converting into OH negative ion. So acid is going to convert into a conjugate base, and base is going to convert into a conjugate acid, because now it has one more extra proton than the parent molecule. That's why it's an acid. So this is a pair, base conjugate acid for HCO3 and for water and hydroxide ion, this is a pair. Let's do the third one. We have hydroiodic acid plus water, give you iodide ion plus hydronium ion. So what's happening over here, if I see Hi after donating the proton is converting into iodide ion, so that means this behaves as an acid, and where the proton is going to the water. And how would I know? Because water is converting into hydronium ion with an extra hydrogen, so water is acting as a base according to Bronsted and Lowry theory. And then after donating the hydrogen, Hi converting into I negative, that means this is conjugate base because this can take up the hydrogen, and then this is your conjugate acid. So for this one, Hi and I negative are acid or conjugate base, and water and hydronium ion are base and conjugate acid pair. So this is how you can solve and figure out the conjugate acid and base pair in any given reaction. So now let's talk about the strength of acid and bases, because we already learned about what are acid and what are bases, how you can classify according to the Arrhenius or according to the Bronsted and Lowry. We already done with this. Now we're gonna talk about how would I know which acid is stronger acid or a weak acid. Basically the strength of acid or base, right? So the strength of an acid depend on the extent to which the acid donate a proton to the water. Means if you have, let's say, HCl, if you dissolve in water, if HCl is donating everything, every proton that we have in HCl, that means this HCl is a strong acid. It's giving it out every proton that it has, right? And the strength of the base depend on the extent to which the base accept a proton from water, right? So it depend on how much extent the base accept the proton, or how much extent the acid donate a proton to water, right? So based on this, we divide acid and base into two categories: strong acid or weak acid, as well as strong base or a weak base, right? So let's go to the next slide, and then we're going to talk about the strong acid first, right? One of the category depending on the strength. So strong acid are those acids that can dissociate in water completely to form a conjugate base and hydronium ion. For example, take this example: HCl react with water. If you dissolve, you're getting Cl negative and hydronium ion. This is your acid, this is your base. Cl negative is your conjugate base, and H3 plus is your conjugate acid, right? And then how would I know this is a strong acid? It given up by the single arrow. So the arrow normally tells you where the reaction is going in which direction. If you have a single arrow, means the reaction is going to get complete, means whatever you dissolve, everything is going to convert into ionic form. And if it's an ionic form, that means proton is already gone from the acid, right? So this is how you can predict, right? Okay, and then what about the strong acid? Strong acid are highly corrosive. That's why it's very dangerous to work with when it's concentrated form, but it's safe to use if it's in dilute solution. And we already know how to make a dilution, right, from the solution chapter. So let's take several of the example of the strong acid for this course. So we have only 6 acid that we can consider as a strong acid, and you have to remember all those 6 acid which are strong, and except these 6 acid, you can say all the other acid can be a weak acid. So nitric acid, sulfuric acid, perchloric, hydrochloric acid, hydrobromic acid, and hydroiodic acid, all 6 are considered as a strong acid. Means if you dissolve any of these acid in water, everything is going to convert into a product side, or everything is going to convert into a ionic form, right? For example, HNO3, if you dissolve in water, you will have a single arrow, means everything is converting into H3O plus and NO3 negative, right? So hydrogen is going to donate it to the water to convert into ammonia, and everything is going to convert into NO3 negative ion. Right. So now let's go to the next slide and talk about the bases. So we already talk about the strong acid. Now let's talk about the strong base. So group 1A and 2A metal ion with the hydroxide ion, we can talk about the base, right? So what a strong base is same as strong acid that completely dissociate in aqueous solution, producing hydroxide ion and cation, the conjugate acid. For example, if you have a sodium hydroxide, sodium belongs to group 1A, so it's a group 1 hydroxide compound, ionic compound. If you dissolve in water, then the solid sodium hydroxide is converting into in their ionic form, sodium plus OH negative, and then the state is dissolved state, aqueous state. And then the single arrow is telling you everything, that whatever the sodium hydroxide in solid form that was present before the reaction, after the reaction everything converting into a ionic form, and whatever the hydroxide you have in the solid NaOH is already present in the ionic form. So it's a complete conversion, right? Okay. So strong electrolyte, if soluble, if this bases are soluble in water, it can act as a strong electrolyte. Means if the ionic compound are soluble, means you have lot of ions present in the solution and can behave as a strong electrolyte because you have a high concentration of ionic form present in the solution. Strong bases are also highly corrosive, similar to the acid when concentrated, and it can be easy to handle or safely handle as if you dilute that concentrated bases, strong bases. Now let's talk about the strong bases like we did for the acid. We have couple of strong acid: barium hydroxide, calcium hydroxide, lithium hydroxide, potassium hydroxide, sodium hydroxide, and strontium hydroxide. So these are the couple of bases which we can treat as a strong bases. So make sure you remember also these 6 bases as well as the strong acid. Now let's move it to the other definition of acid and base, which we call as weak acid or a weak base. So we're gonna talk about together about these two things. So weak acid and weak bases are those acid and base which normally dissociate very little in water, right, or very minute in water, and produce few ions in aqueous solution. For example, acetic acid, CS3 COOH, acetic acid. When dissolved in water, you get hydronium ion because acetic acid is an acid. So this hydrogen, acetic acid is the proton donor is gonna go over here, and water is going to convert into a hydronium ion, and then acetic acid itself is going to convert into acetate ion, right, with a negative charge on this oxygen. But how would I know this is a weak acid? Because of this two-sided arrow, back and forth arrow. So this is an equilibrium, means whatever acid we dissolve in water, everything is not converting into a hydronium ion or acetate ion, right? Some of them is, the reaction is still going backward too with the same pace. So let's assume if I use 2 moles of acetic acid, it's not possible for all the 2 moles of the acid is going to convert into a product, right? So that means this is a weak acid. And then if it's a weak acid, reactant concentration is always higher than the product, because the name is saying weak. So that's why acid wants to be present in its original form rather than in a dissolved form. So let's take an example. We can also test whether the acid or base are weak acid or a weak base. Let's say if I dissolve any strong acid in a solution, and if I put an electrode in the solution and I put a bulb on it and make the circuit complete, if the acids are strong, that means you have lot of ions present in the solution, and if I turn on the switch, then you will complete the circuits, because the ion can carry out the electric current from one electrode to the second electrode, and then the circuit is complete. Then the bulb will the, the bulb will shine bright compared to the weak electrolyte. Weak electrolyte means you don't have enough ions in the solution, for example weak acid, and if you turn on the switch you don't have enough ions to complete the circuit, even though you can still complete the circuit, but it's not as much as in the strong electrolyte. That's why the light of the bulb is not that as bright. It's like a dim light coming out, right? But if the solution is a non-electrolyte, we already talk about non-electrolyte means no ions present in the solution, so there is no complete circuit forming. That's why you don't see any color or light coming out from the bulb, right? So this is how you can also decide whether the acid are weak or a strong acid. There's a couple of example of weak acid, like we already used one of the acid, acetic acid. Citric acid is also a type of weak acid, right? So there are organic acid like acetic and citric acid. There are some inorganic acid like carbonic acid, H2CO3, phosphoric acid, hydrofluoric acid. They are weak acid, right? And you can assume that any acid that is not part of the 6 strong acid, you can assume that acid is a weak acid, right? And then let's talk about the ammonia. Ammonia is an example of a weak base. And how would I know it's a weak base? So let's see the reaction what's going on when you dissolve ammonia in water. You will see an equilibrium reaction, right, by looking at the back and forth arrow. So what's happening over here, the ammonia is not converting completely into ammonium ion, right? And that's why this ammonia is a weak base, because you're not producing more ammonium ion. So that means ammonia is not converting completely to ammonium ion, right? So this is how you can figure it out whether the base is a weak base or a strong base, by looking at the arrow over here. So now let's talk about the Le Chatelier principle. According to this principle, any reaction which is in equilibrium, let's take an example. A plus B is in equilibrium and producing C plus D. That means at equilibrium the reaction is going back and forth at the same rate and the concentration are constant on the product as well as the reactant side. So if you change or disturb this equilibrium condition by removing any of the thing from the reactant or by putting anything on the product or vice versa, you are disturbing the reaction, the chemical equilibrium of the reaction. So the reaction will shift in the direction that counteract a disturbance. For example, if I take out the B, if I remove B from the reactant, that means I am giving out some disturbance to this reaction which is at equilibrium. Then the C and D will react together and the reaction will move it backward to produce more B, because you disturb the concentration of B, right? But if I take out a C from the product side, then the reaction will go towards the right hand side, because I did the disturbance on the product side. So the reaction has to counterbalance that disturbance in the concentration of C by moving the reaction on the right hand side. And this Le Chatelier principle is very important for weak acid as well as weak base reaction, because that is also is in equilibrium. So let's take an example of ammonia that we already did, and we know is a weak base. We already saw its reaction with water, and then try to apply the Le Chatelier principle on this reaction and then figure it out and try to solve these couple of questions that we have on this slide. So the question number 1 says, write the equilibrium reaction for ammonia in aqueous solution. Second says, if an additional hydroxide ion are added, will the reaction shift to the right or left? You have to explain. The third one says, if some ammonia molecule are removed from the solution, will the reaction shift to the left or right? Explain. So let's try to do these problems one by one on the other slides and then try to understand how you can answer these type of problems. So the problem 1 says, write the equilibrium reaction for ammonia. So this is your ammonia, react with water. We have hydroxide ion and ammonium ion with an equilibrium sign in between, because ammonia is a weak acid, weak base, right? So we already done the equilibrium reaction for ammonia. Let's go to the next slide and try to solve the other part of the question. So part B says, if an additional hydroxide ion are added, will the reaction shift to the left or right? So hydroxide ion present in the product side, if I put more hydroxide ion in there, so that means the concentration of the hydroxide is getting increased on the product side. So to counterbalance this increase of the hydroxide on the product side, the reaction will turn on and then go back to the reactant side. So that's why it goes to the left hand side, right, according to the Le Chatelier principle, to counterbalance this increase in concentration of the hydroxide ion. Let's go to the third part. The third part says, if some ammonia molecule are removed from the solution, so we have an ammonia on the reactant side, if I remove it from the reaction medium, so that means I'm decreasing the concentration of the ammonia in the reaction mixture on the reactant side, and the reaction will think about, okay, we don't have more, we have less concentration of ammonia in the reaction medium, then the reaction is going to convert or move it to the left side one more time. Why? To replace the removed ammonium ion or ammonia that we took out from the reaction medium. So the reaction will move to the left, and the reaction try to make more and more ammonia. So that's why the reaction move to the left. So now we're going to talk about a new subtopic, which is a pH. So in this topic, we're going to talk about what is pH, what's the importance of learning about this concept of pH, and where we can use this concept of pH and where we can apply. So let's start with this concept. So pH is nothing, is a measure of the concentration of the hydronium ion in an aqueous solution. So how much amount of the hydronium ion or how much concentration of the hydronium ions are present in a solution, we can easily measure the pH of that solution, right? If you have, and if you can see this kind of box, and if you have something written within the box, for example, the closed box from both sides, if you have something written in between and like between them, this is shows the concentration of that species, chemical species, you can say. So the hydronium ion is written in between the two boxes, closed box. That means we are concerned about the concentration of the hydronium ion. Similarly, for OH negative ion, if you have a box surrounding it, that means we are talking about the concentration of the hydroxide ion. And in concentration, the most common concentration unit that we normally use is molarity, which is moles per liter. So how many moles of the hydronium ion are present in per liter of the solution, or how many moles of the hydroxide ion present per liter of the solution, that will give you the concentration of both the species. So we will learn, if the pH is less than 7, the solution is going to be acidic. The concentration of the hydronium ion is higher than concentration of hydroxide ion. If pH is more than 7, the solution is going to be the basic one, and in this case hydronium ion concentration is less than the hydroxide ion concentration. And the last one, if the pH is exactly equal to the 7, the solution is neutral. That means the concentration of both of them are equal in the solution. So right now, just remember this thing. We're going to learn about all the concept. Why the pH has some number 7, right? Why we have a special number, and how would I know by comparing the hydronium ion and hydroxide ion concentration? How would I know this is acidic or basic? So let's go to the next slide, and then we're going to talk about all these concepts that we have on this slide right now. So before we go and understand what's the concept of pH and how you can apply the concentration of hydronium ion and hydroxide ion concentration to figure it out what's the pH of the solution, let's talk about the importance of the pH, why we need to study about the pH. So understanding the pH is very important in terms of medicine or in terms of the physiology of the body, right? So we know we have a blood in our body, and then the blood has a pH of, or that range of the pH of our blood is 7.35 to 7.45. So right now just remember this term, and then we're going to learn about what's this number, right? Why pH has different number. But right now just focus on this. If the pH of the blood goes lower than this number or higher than this number, then we have a problem, because the pH of the blood cannot be changed, or it's gonna be a very big problem, right? So if the pH of the blood goes lower than this number 7.35 for this range, then you will have a disease we call as acidosis. Means you will have more acidic character to the blood compared to the basic one, right? And if the pH value goes higher than this range 7.45, then you have one more condition called alkalosis, right? And both of these conditions can be very dangerous and can be very life-threatening. So that's why understanding the concept of the pH and how to maintain that pH in the blood is very important, right? And we also have the other fluid in our body that have the specific normal pH value. Let's go to the next slide and then see what are the different part of our body and what their pH are. So now what we are seeing over here is a table that says the pH of some normal body fluid, and we have some numbers, right? So for gastric fluid, pH is very low, 0.5 to 2, saliva 6.5 to 7.5. So, and blood, we only talk about 7.35 to 7.45 is the range. So, and we can see over here different part of the body have different pH, right? So if the pH is changed for that particular part of the body, then there's gonna be some problem, some condition, and can cause some kind of disease. So the pH value are very important. So now let's start with the concept of the hydronium ion or a hydroxide ion, right? And then we're gonna learn about why the concentration of one species compared to the other one tells you have high pH or low pH, right? So let's understand the concept. So we're gonna start with the term called KWN, autoionization of water, and we're gonna learn about what does it mean. So let's take, if I have a water, a pure water, right? In here you have water molecule in there, right? And what's special about the water molecule? Water is an amphoteric substance. If you remember from the couple of slides that we did, the first couple of slides, amphoteric substance. And what is amphoteric substance or molecule? That can act as acid as base both at the same time, right? So if you have a glass of water, pure water, right, and then in that pure water a very minute amount of the water molecule can react with each other, because one of the water molecule can act as an acid, another molecule can act as a base, right? Because this is an amphoteric and they can do some kind of reaction, acid and base reaction. This we call as autoionization of water. They are doing the reaction by themselves, right, without the help of any other thing. So one of the molecule from the pure water can act as an acid, another one can act as a base. So if this is an act as an acid, proton is going to go from here to the oxygen of the base, then you're going to make an hydroxide ion and hydronium ion, right? So that means whenever any two molecules of water react by autoionization, you're going to make a hydroxide ion and hydronium ion, and this is called as autoionization of water. And then experimentally it's been seen that the concentration of the hydroxide ion and concentration of hydronium ion, if I multiply them together, you will have a constant number. Let's go to the next slide and then talk about this thing a little bit more. So it's been, like I said, experimentally determined in pure water at room temperature 25 degrees Celsius. It's been seen that, or it's been found out that because of the autoionization of water, the concentration of the hydronium ion and concentration of the hydroxide ion, they are same, and what the number is 10 raised to power 1.0 10 raised to power negative 7 molarity. This is the concentration for both of them. And if you multiply the concentration of hydronium and hydroxide ion, you will always get a constant number, which is 1.1 times 10 to the power 14, because the concentration of H3O plus is 1 times 10 to the power negative 7. OH negative is same, 1 times 10 to the power negative 7. If you multiply these two numbers, you're gonna get 1 times 10 to the power negative 14. And this 1 times 10 to the power negative 14 we call as Kw, a constant. We call as ionic product constant for water. This number cannot be changed if you multiply the concentration of hydronium and hydroxide ion. Right. So make sure you remember this equation, because this is the equation that we're gonna use to solve some of the problem. So I can write the equation over here. Kw is equal to the concentration of OH negative ion or concentration of H3O plus ion. This is your equation, and we already know what's the Kw value is 1.0 times 10 to the power negative 14. Right. So that means to maintain this number constant, because this is a constant number, if one thing goes up, another thing should go down with the same value, so that the multiplication number won't change, which is a constant number. For example, if I have any number 4 times 3, what's the number? 12. Assume 4 is the concentration of hydronium ion, 3 is the concentration of OH negative ion, and this is your Kw, 12. Right. If I increase, or let's say decrease, the concentration of hydronium ion in a solution, let's say it's decreased from 4 to 2. Right. So how many times it decreased? It decreased 2 times. Right. So to maintain this constant number 12, which is our Kw for this example, should the hydroxide ion concentration will increase or decrease? It's gonna increase by the same amount 2 times. So 3 times 2, 6. 6 times 2, 12. This is the same number, which won't increase or decrease. It remain constant. So that's why you apply the same concept over here. If the concentration of the hydroxide ion is going to increase, then the concentration of the hydronium ion should decrease to maintain this number as constant. Right. And then from this equation we can also figure it out the concentration of hydroxide ion if the concentration of hydronium ion is given, or vice versa. Right. Now let's try to grab some more concept from the autoionization of water. What we learn the ionic product of water is equal to the concentration of H3O plus and OH negative ion. Right. And we already know the value of Kw, 1.0 10 to the power negative 14. Right. We already know this concept of autoionization of water, right, or the ionic product constant. So now let's take an example over here. If I have a solution, right, and if I say the concentration of H3O plus ion in this solution is higher compared to the OH negative ion concentration, which is lower, this solution is acidic or basic. How would I know? How are you gonna tell whether the solution is acidic or basic? So if we get the concept of the Bronsted and Lowry concept or the Arrhenius concept, according to those two theory of the acid and base, we know if you have how you're gonna produce this H3O plus. If you have more H3O plus, means somebody give it out the proton in there, right? That's why the water is going to convert into H3O plus. And if somebody is giving out the proton in the solution, that means, and if the concentration of H3O plus is higher, that means you have lot of H3O plus ion compared to the hydroxide ion. And how it is possible? When you have lot of H plus ion present into the solution. And if you have lot of proton present in the solution, that means you have lot of acidic molecule. That makes sense, because if you have a lot of molecule that can act as an acid, that's the only region that you can have lot of proton. And if you have a lot of proton, that's the only region you can have the lot of hydronium ion. So that means if you have high amount of concentration of hydronium ion, means you have lot of acidic molecule present in there. So that means the solution is acidic, right? So this is how you can, and then vice versa, if you have less amount of. And so let's take one more example. In this solution, if you have high concentration of hydroxide ion, low concentration of hydronium ion, so that means you have less amount of the molecule that can act as an acid compared to the molecule that can act as a base. So this means this solution is basic in nature. So this is basic solution. So this is how you can compare. So let me give you one more example of here. The concentration of H3O plus in any solution. Let's say this is the solution. In this solution, the concentration of H3O plus is 1.0 10 to the power negative 9 molar. In the same solution, the concentration of OH negative ion 1.0 times 10 to the power negative 5 molar. You have to tell us whether this molecule is, or this solution is acidic or basic. So if we compare the numbers, of hydronium ion concentration of OH negative ion concentration, which number is bigger? So if I compare these two numbers, the hydroxide ion concentration, this number is bigger, right? Because the exponent part is less negative. So that means if the concentration of hydroxide ion is bigger or higher in a solution compared to the hydronium ion concentration, so that means this solution is your basic solution, because you have those molecules that can produce more OH negative ion compared to the one that can produce proton. So this solution is basic. Same thing if I give you one more example. For this solution, H3O plus ion concentration is 1.0 times 10 to the power negative 3, and OH negative ion is 1.0 times 10 to the power negative 11. So in this solution, hydronium ion concentration is higher compared to the hydroxide ion concentration. So H3O plus is higher. So this solution is your acidic solution. So by looking at the number of the concentration of both of these species, you can figure it out whether the solution is acidic or basic. Now let's try to do some of the problem based on the concept of the autoionization of water. So the problem says, what is the hydroxide ion concentration, means OH negative ion, for an aqueous solution with a hydronium ion concentration? H3O plus ion concentration is already given for you, which is 1 times 10 to the power negative 3 molar. So we have to use the autoionization of water concept. We have to use this concept, which is Kw is equal to the concentration of H3O plus times OH negative ion, right? And we already know the value of Kw, which is 1.0 times 10 to the power negative 14, right? So this is the equation, and we have to figure out the OH ion concentration. So divide both sides of this equation by OH negative ion, the H3O plus ion, hydronium ion. So hydronium ion is gonna get cancelled, and you will left with OH negative ion equal to 1 times 10 to the power negative 14 divided by hydronium ion, and plug in the number of the hydronium ion. When you solve it, you're gonna get this 1 times 10 to the power negative 11. So if I ask you whether this aqueous solution is basic in nature or acidic in nature, how would I know? So you have to compare the concentration of both of them, hydronium ion and concentrate the hydroxide ion. So the hydronium ion is already given, which is this number, and hydroxide ion concentration you just solve it for. So out of these two number, which number is bigger? The hydronium ion concentration is bigger, this number. So that means this solution is acidic in nature. You have acidic solution. So this is how you can figure it out. Let's try to do another example on the next slide. So let's try to do this one. What is the hydronium ion concentration? You have to figure it out, the H3O plus concentration in this problem for an aqueous solution with an hydroxide ion concentration of 1 × 10⁻⁻10. So again use the same equation. We need H3O plus ion, divide both sides by OH negative ion. This will cancel. You will get H3O plus equal to 1 × 10⁻14 over OH negative ion. Plug in the value, you will solve. For hydronium ion, you're gonna get 1 × 10⁻⁻4. Right. So this aqueous solution is acidic or basic? So let's compare the number again for both of them. Hydroxide ion has 1 × 10⁻⁻10. Hydronium is 1 × 10⁻⁻4. So again, for this particular aqueous solution, hydronium ion concentration is higher. So this solution is again as acidic solution. Right, so this is how you can calculate if one of the species is given. If we ask you for the other species like hydronium and hydroxide, you can solve using this autoionization of water equation. And you can also predict whether the solution is acidic and basic once you figure it out one of the unknown and compare with the given number, right? So you can predict the solution is acidic or basic. Now let's talk about how we can get the pH, because in the beginning we talk about the pH value, right? And then we had some numbers 1, 2, 3, 4, 5, pH 1, pH 4, right? For the blood we have 7.35 to 7.45. So how would we get that number? So we get that number from this equation, which we have pH equal to negative log with a base of 10 hydronium ion concentration. So that means you need to have the hydronium ion concentration somehow before you can use this equation and get the pH number. And then for the pH number pH is a scale. We have a scale that goes from 0, 7 to 14. So this is we call as pH scale. If the number comes out to be below than 7, this is acidic. If the pH number come out to be more than 7, base. And then one more thing that you need to remember, the lower the number closest to the 0, the more acidic is the solution. So that means 4 and 5 pH. 4 is more close to the 0 or is a less number compared to the 5. That means pH 4 is stronger acid compared to the pH 5. Same thing apply for the base. Bigger the number, more basic is the solution. So if you have pH of 8 and 11, a pH of a solution that has a pH of 11 is more basic compared to the solution that has a pH of 8, right? And if the pH number come out to be exactly 7, if pH is exactly 7, that means the solution is neutral, right? Or there's one more concept on this, that we can say if pH is less than 7, I can say the concentration of hydronium ion is bigger or higher compared to the concentration of the hydroxide ion, right? The second thing is if the pH is more than 8, if the number more than 7, I would say, in this case the concentration of the hydronium ion is less than hydroxide ion, because the solution is basic, because we know if the pH is more than 7, the solution is basic. In which condition the solution is going to be basic? If the concentration of the hydronium ion is less compared to the hydroxide ion, that's why it's going to be basic. If the pH come out to be exactly 7, I can say the concentration of the hydronium ion and hydroxide ion, they are equal, right? It depend on how many moles of the acid you have to have the same moles of base, so they can neutralize each other and the pH come out to be exactly 7, right? So this is a concept that you need to remember about the pH, right? Whether it's a number or whether you have to compare the hydronium ion or a hydroxide ion depending on the pH number. So let's take an example for pure water. The pH is, for pure water, if I say what's the concentration of hydronium ion for pure water, we already learned about the autoionization of water. The concentration is 1 times 10 to the negative 7, right? So plug it that number over here, because pH is equal to the negative log of hydronium ion concentration. When you plug it, use your calculator, plug in this number, and then you will end up with a number called 7. So that means for pure water, the solution is, or pure water is neutral in nature. So now let's talk about the scale. We already talked about the scale. The scale goes from 0, 7 and 14, and if the pH decreases, hydronium ion increases. If the pH goes lower, that means hydronium ion increases. Let's talk about two examples. In one of the solution, hydronium ion is 10 to the negative 6. If we use the formula, or the formula for the pH, negative log of H3O plus, and if you plug this number over here and use your calculator, you will come out with the pH number of 6. And for any other solution, the concentration of hydronium ion in that solution came out to be, let's say, 1 times 10 to the negative 4. If you use the formula again, you will end up with the pH value of 4. So solution A or solution B, how much difference in the pH value? We have a pH value of difference of 2. B has 4, A has 6 pH value. But even though they differ by a 2 pH unit, but the concentration of the hydronium ion between the two solution is 100 times, because pH is a logarithmic graph or logarithmic scale. So if the unit increase by 2, then the concentration should be increased by or decreased by 100 times, right? So pH is a logarithmic scale. Each unit is 10-fold change in the hydronium ion and hydroxide ion concentration. If you have a pH, for example, 3 and pH 2 for any two solution, then the concentration difference between the hydronium ion or hydroxide ion concentration is 10 times, even though the pH unit is different by just 1 pH unit. So you have to make sure you know this thing. Now let's take an example and try to solve some of the problem on the pH equation. What's the pH of a solution with the hydronium ion concentration is already given, which is 1 times 10 to the negative 9 molarity. And you have to tell, once you figure out the pH, you have to tell whether the solution is acidic, basic or neutral. So we know pH is negative log of H3O plus ion, and the H3O plus ion concentration is already given. Just plug in the number, use your calculator, you will end up with 10 to the, you will end up with 9.0. And I know if the pH is more than 7, the solution is basic. Now let's try to do one more problem. What is the hydronium ion concentration, H3O plus, of a sample of a stomach acid with a pH of 2? So now we have a different problem. So in this problem, the pH is already given for you and it's asking for the hydronium ion concentration. And we know what's the formula for the pH. pH is equal to negative log of H3O plus. So what we have in this problem, the pH is already given. You have to figure it out the hydronium ion concentration. How would I do that? So we have to reshuffle this equation a little bit. So after reshuffling this entire equation, I can say H3O plus concentration is equal to 10 raised to power negative of the pH value. Right? So this is not a new equation. I just reshuffle it, the original equation. So let's try to solve this problem. So H3O plus concentration is gonna be 10 raised to power negative of the pH number. What's the pH number given? 2. So H3O plus concentration is equal to 10 raised to power negative 2, or you can write the same number as 1 times 10 raised to power negative 2, because it doesn't matter if you multiply any number with 1. Right? So this is how you normally do it. So if you have any pH number given, just use this formula and then use your calculator. You will end up with your answer with the hydronium ion concentration. So now let's try to do a couple of more problems just to build some more concept on the pH value. So let's take an example. If you have a solution, right, and then for this solution the hydroxide concentration is given, which is come out to be 1 times 10 raised to power negative 6 molar, and you have to tell us what's the pH of this solution. And once you get the pH, whether the solution is going to be basic, acidic, or neutral. Right, so let's try to figure it out how to get the pH if the hydroxide ion concentration is given instead of hydronium ion concentration. So how to get the pH? pH is, the formula for pH is negative log of hydronium ion concentration. Right, if I know the hydronium ion concentration, I can plug in over here and get the pH of that solution. But the problem over here is, for this solution the hydroxide ion concentration is given, not the hydronium ion, and we cannot use this number over here. So what we need to do, we have to first figure it out what's the hydronium ion concentration for this solution. And how would I do that? So we have to use the equation Kw, autoionization of water, H3O plus OH negative, and then we know the value of Kw, which is 1.0 10 raised to power negative 14 H3O plus and OH negative ion. And we need to figure it out the H3O plus ion, because in pH we have H3O plus ion. Divide both sides by OH negative ion. This will get cancelled. Then H3O plus concentration come out to be 1.0 times 10 raised to power negative 14 over, what's the concentration of the OH negative ion given? 1.0 times 10 raised to power negative 6. If you divide these two numbers, you will end up with 1.0 10 raised to power negative 8 molar for H3O plus concentration. And now we have hydronium ion concentration in our hand, and I can use this hydronium ion concentration directly into the formula. Right, so let's plug in the number. pH is equal to negative log of 1.0 10 raised to power negative 8, and when you solve it using your calculator, you will end up with 8.0 pH. And the time I see the pH value is more than 7, I know this is a basic solution. So the solution is basic in nature. So this is how you can solve another type of problem on the pH if the concentration of the hydronium ion is not given, instead the hydroxide ion concentration is given. So first you have to convert that hydroxide ion concentration to a hydronium ion concentration using the autoionization of water equation, and use the hydronium ion again into the regular equation of the pH value, and then you can get the pH number. So this is another type of question. Make sure you practice this type of problem too. Now let's talk about the third subtopic of this chapter, which is acid-base neutralization reaction. So in this topic, we're going to talk about if you have an acid, if you react with a base, what type of reaction you can get, and what are the products that you can get. Right. So let's get started with. So acid-base neutralization reaction is that reaction where you mix an acid with a base and a neutral product is formed. That's why the name is neutralization reaction. And neutralization reaction is also called as double displacement reaction, right? For example, if you use an antacid, whenever you have an acid, extra acid like present in your stomach, antacid can react with an acid and neutralize the extra acid, right? The acidity of the body. So in neutralization reaction, you always mix an acid with a base. You get an ionic compound, basically a salt and water. This is basically a neutralization reaction for acid and base, and we're gonna just use several examples to see what kind of product they can make and how they can neutralize each other, the acid and base. So let's go to the next slide and then try to understand different types of reaction or different types of bases that we can use in acid neutralization reaction. So what are the common bases that we use in neutralization reaction? We can use hydroxide ion because hydroxide ion is a base, hydrogen carbonate and carbonate ion. So we're gonna use the reaction with acid with each of these bases. So let's try to do it one by one. So let's start with the hydroxide ion. So we are going to use a sodium hydroxide as an example of hydroxide ion containing base and react with an acid. In this case, we are using hydrochloric acid. So when you mix these acid and base together, you're going to make water, right? That we already know, and you make an ionic compound. Ionic compound, which is a salt. So what happened during this reaction is this is sodium hydroxide is aqueous. So what happened over here? It should present as Na plus aqueous plus OH negative ion aqueous plus HCl is also in aqueous. So it's present in ionic form aqueous and Cl negative ion aqueous, right? So this is your reactant. So what happened over here, the OH negative ion from the base, H plus ion from the acid react with each other and they make water as a product, which is a neutral. That's why this is a neutralization reaction, because base is OH negative, acid is H plus. What about the other two component that is present in the reactant? One of them is metal, sodium ion, second one is chloride ion. So they combine together to make an NaCl, but the thing is that NaCl is also present in aqueous form. So if the NaCl is in dissolved form, it doesn't remain as NaCl, it remains as Na plus Na and Cl negative, aqueous. So what basically happening in neutralization reaction, only the proton and hydroxide ion are actually reacting and making a new product. This is the only two components of the reactant that are basically doing a chemical reaction. But what about the sodium ion and chloride ion? If you can see on both sides, reactant as well as product, they are present the way it is, or it was present in the reactant. Na plus aqueous, Cl negative aqueous. In the product, Na plus aqueous, Cl negative aqueous. So they basically doing nothing. They are not doing any reaction with each other in neutralization reaction. That's why we call those kind of ions as spectator ions. They are just present as a spectator. They are not doing anything, right? So remember this thing. If you see any problem, a question says what are the spectator ions, you always have to see those component of the reactant that doesn't change during the reaction. Those ions are called spectator ions. Now let's talk about the neutralization reaction with an acid, which is polyprotic. As the name is saying, poly means many, protic means which can give out the proton. Acid, so we know acid are which can donate a proton. So there are some polyprotic acid means which those molecule or compound that behave as an acid that can give out multiple proton instead of just one. For example, hydrochloric acid is monoprotic. Mono means hydrochloric acid has just one proton to donate, but polyprotic can have multiple, more than one. So sulfuric acid is an example. We have 2 hydrogen that can be donated. Phosphoric acid has 3, citric acid has 3. So these are called polyprotic, and we're going to take an example of any one of these polyprotic acid and then see how they can react with the base, what kind of reaction they do. Let's go to the next slide. So we're going to take an example of again sodium hydroxide as a base, and in this case polyprotic acid is a sulfuric acid. We have 2 hydrogen atoms that can be donated. So once the reaction is done, again you're gonna make water. We already know the product, and you're gonna make one ionic compound, right? Ionic compound. So all of these are present in aqueous phase, right? So what's happening over here, you have one OH and 2 hydrogen, right? But in the product side you have 2 sodium. In the reactant side you have 1 sodium. So you have to balance the sodium atom, right? According to a law of conservation of mass of matter, you have to put 2 in the front, and then the time you put 2 in the front, you have to put 2 in the front of water just to balance the hydrogen and oxygen again, right? So this is how the reaction happen whenever you use a polyprotic acid. So the actual reaction that is been happening in here is 2 proton from acid react with 2 hydroxide ion from the base NaOH, right? We have 2 in the front. So when they're reacting, they are making 2 molecules of water, right? The ratio is 1:1. And then what are the spectator ions? So spectator ions are sodium, because in this thing sodium is present as Na+, sulfate is present as SO4 2 negative. They are aqueous, so they are dissolved in ionic form. In the product side, again their ionic compound dissolve in aqueous phase on water, so they are present like this, 2Na+, SO4 negative 2. So they didn't do anything, they just present in the solution, they are not doing any reaction. So spectator ions are sodium and sulfate. So now let's try to do one problem based on the concept that we just learned about the neutralization reaction. So we're going to solve one problem. It says answer all of the question that is been asked on the bottom for the reaction between hydrobromic acid and potassium hydroxide. So if HBr react with KOH, we have to answer all the problem or all the question that is been asked. So we're gonna do it one by one, right, on the next slide. So let's go to the next slide. So which solution is acidic? So we already know the reaction HBr react with KOH, and we know what's the product, water and an ionic compound, in this case KBr, right? So this is your actual reaction. So which solution is acidic? Hydrobromic acid is acidic because it has the proton that it can donate. This is an acid. What ions are dissolved in the acidic solution? So if this is the acidic solution, what are the ions? H+ and Br negative from here. Which solution is basic? Potassium hydroxide is a basic. What are the ions? K+ and OH negative ion. Write the complete balance equation. So for balancing, you have HBr aqueous, KOH aqueous, water, and what is a liquid, and KBr aqueous. So we already done it on the top over here. What is the net reaction? So the net reaction is that reaction which is actually happening in this neutralization reaction. So what's the actual reaction happening? The H plus from the acid react with the OH negative ion from the base, making water. So this is the reaction that is actually happening, which is a net reaction. And what are the spectator ions? Like I already told you, spectator ions are the ions that are unchanged during the reaction. So what are the spectator ions? Bromide and potassium, right? So KBr. So in this reaction, KBr is present and K plus and Br negative. In the reactant side also, Br negative and K plus. So they haven't done anything. They are just present in the ionic form before the reaction as well as after the reaction. So this is how you can answer any kind of question depending on the neutralization reaction. Let's do one more problem. On the neutralization reaction, what's going to be product if you react hydrofluoric acid with aluminum hydroxide? So you have HF react with AlOH3. So what you need to do, you have hydroxide ion, right? So if these are in aqueous form, AQ, so this is present as H plus and F negative, and this one is present as Al plus 3 and 3 OH negative ion, right? If I just dissolve this thing into ionic form, so what's happening over here? H plus is going to react with OH, but the problem is you have just one proton reacting with 3 hydroxide ion, so you have to put 3 in the front. So now you have 3 proton, 3 fluoride, right? So now you're gonna make 3 molecule of water, and now the charges, each aluminum is plus 3, you have 3 fluoride ion, each fluoride is -1, so you can make AlF3, and now F3 is present as Al plus 3 and 3F negative, because this is again in aqueous, right? So this is the actual reaction that is happening over here. This is the reaction, complete reaction, but what's the actual reaction? Actual reaction is this 3H plus 3OH negative gives you 3H2O. Thus your net reaction, which is actually happening. But what are spectator ions? Spectator ions are fluoride ions and aluminum ions. This is your spectator ions. So this is how you can figure it out, right? So we did 2 examples, so make sure you practice both of these examples to figure it out, net reaction or spectator ions. So now we're done with the neutralization with the hydroxide ion. Now we're going to talk about the neutralization reaction with an acid with 2 bases, hydrogen carbonate HCO3 negative and carbonate CO3 negative 2. That's your -2, right? So we're going to talk about these 2 things and see how they react with an acid. So before we go, we know both of them are weak bases and they are frequently used in neutralization reaction. So these kind of bases normally being used in the neutralization reaction, and when they react with an acid, they always produce water and carbon dioxide. So you're gonna get 2 products this time, right? So this is an extra, a gas is produced. So let's do the next slide and see the reaction, actual reaction that is happening. So reaction of baking soda with vinegar. Vinegar is your acetic acid. So that's your acetic acid. React with baking soda, sodium bicarbonate. So what you have over here, you have Na plus and HCO3 negative, and over here you have H plus and C2H3O2 negative. When they react together, what's actually happening, this H plus is going to react with the base and Na plus is going to react with anionic form. So you're gonna get water, and then the ionic compound, this is your ionic compound, and you're gonna get carbon dioxide. But like I said, when H plus react with SCO3, you're gonna make H2CO3, and this carbonic acid is not stable, and then it's gonna decompose into H2O and CO2. So this is your product. That's why when proton react with sodium bicarbonate or a bicarbonate, you always produce a carbonic acid. But because of instability of this compound, you get a final product as water and carbon dioxide along with the ionic compound. Right. Same thing happened with the carbonate ion. You need 2H plus ion to neutralize this 2 negative ion. So you're gonna make H2CO3, and this is so unstable that it decomposes into water and carbon dioxide. And whenever you're doing this reaction, let's say for in a test tube, you will see a lot of bubbles, and this bubble indicate carbon dioxide gas. Right. Let's try to do one more example on the topic that we just learned about the carbonate and bicarbonate. So the problem saying write the complete balance equation for the reaction between hydroiodic acid and potassium hydrogen carbonate. So hydrogen iodide react with potassium hydrogen carbonate. What are the spectator ions? What is the net reaction? So we know these all of them are present in aqueous. So this is present as H plus ion or I negative ion. This is present as K plus and HCO3 negative one. So what's actually happening is H plus proton is going to react with hydrogen carbonate and is gonna make H2CO3, but it's so unstable. The final product that you're gonna see is water and carbon dioxide, which is a gas, and you will see the bubble is coming out. And then you will get one ionic compound between K plus and I negative. They can combine together and form potassium iodide, and this is again in aqueous, so that means this is still present in K plus and I negative form. So that means the K plus and I negative doesn't actually reacted with each other. They are present before the reaction as ionic form. After the reaction is still in the same form. The chemical composition doesn't change. That means they are just there as a spectator ions. So what's the net reaction? Net reaction is H plus HCO3 negative. Then these are the two products. This is the actual reaction that is happening. Right. So yeah. So we are done with the example. So make sure you practice a lot for the neutralization reaction. Read your book if you have any doubt. Right. Try to get the concept. Now let's go to the next topic, our last topic for this chapter, which we call as buffer. So in this topic, we're going to talk about what is buffer, what's the importance of this buffer in our body, and why we need this buffer. Right. So buffer is a solution that resists changes in the pH when a small amount of acid and base are added. For example, like our blood. The blood in our body has a pH range of 7.35 to 7.45, right? The pH value. But as we know, we normally eat a food that may be acidic in nature or may be basic in nature, right? So by eating the food, we might change the pH of the blood, but it doesn't happen that regularly, right? Why is the case? Why the pH of the blood doesn't change even though you eat any acidic food or basic food? Is because blood is a type of a buffer, right? It resists any change in this pH value even though you are eating an acidic food or basic food, right? So we're gonna learn how does this work, right? Why does the pH of the blood doesn't change, or the pH of the buffer or any solution doesn't change if that solution is a buffer, right? And then because of the buffer ability of the blood to act as a buffer, it can help to maintain the homeostasis in our body and prevent the acidosis and alkalosis, right? In decreasing or increasing the pH value of the blood. And we already talk about this thing. These are life-threatening condition. So it happened because of the buffer nature of the blood. So let's talk about the component of the buffer before we can go and see how the buffer actually work. So the component of the buffer is made up of a weak acid and its conjugate base in similar concentration, right? So if you have any weak acid and if you put a conjugate base of its weak acid, you make a buffer, right? And then we have two special term called, one is called pH range, one is called buffer capacity. pH range is maintained by a buffer depend on the identity of the weak acid. So depending upon which weak acid we are using in a solution, in a buffer solution, we can tell what's the range of the pH for that buffer solution depending on which acid we use to make the buffer, right? And then we have another term called buffer capacity. Buffer capacity tells how much concentration of the buffer component you have in that solution, right? How much concentration of the weak acid or its conjugate base are present, right? Higher the buffer capacity is very difficult to change the pH by adding acid or base, right? So let's see a couple of the example of the common buffer that we normally use. One of them is acetic acid and acetate buffer. So this is your weak acid, this is your conjugate base, acetate ion. So this is acid, this is conjugate base. Once the acid is removed, you will get a negative. And this is a common laboratory buffer that we use in chemistry or any science laboratory. Then we have carbonic acid and hydrogen carbonate buffer. Carbonic acid is H2CO3, then its conjugate base will be one less hydrogen, which is HCO3 negative. And this carbonic acid is buffer present in our blood. This is the main buffer that maintain the pH value of our blood, so that it doesn't fluctuate too much, right? And then we have dihydrogen phosphate or hydrogen phosphate buffer. This is also a common laboratory buffer too. So let's try to understand how this buffer system work, right? We already know it's made up of weak acid and its conjugate base, but let's try to understand how does it work. So whenever you use a weak acid, we know what are weak acid that doesn't give out all the protons in the solution. So there will always be a equilibrium. So weak acid dissociate in water and make a conjugate acid A negative by providing the hydrogen to the water to make hydronium ion. So buffer is weak acid and its conjugate base. This is the combination. So let's see how does it work. For example, if I put more H3O plus in this solution from outside, if I increase the concentration of the hydronium ion, that means I'm decreasing the pH because hydronium ion I'm putting more acidic. So what happened over here, the extra hydronium ion that you are putting in the buffer system is going to react with the conjugate base, and the reaction will go towards the left side. That means you are making more weak acid, the unionized form, right? So that means the pH of the buffer is not going to increase or decrease, because whatever the extra acid that you put in the solution is already been used by the conjugate base to convert that extra acid into a weak acid, into a non-ionized form. So that's why the pH doesn't increase. Let's do one more example. Instead of adding more H3O plus, if I add hydroxide ion, so what's going to happen? If I put more hydroxide ion, means I am taking out the H3O plus from the solution, right? Because if I put the hydroxide ion, is going to neutralize by the hydronium ion, and there is no more hydronium ion present in the product side. So that means you have less amount of the hydronium ion present. So in this case, the reaction will go towards the product side to make more hydronium ion, right? So that means there is no effect of the hydroxide ion on the pH value of the buffer, because if you put more hydroxide ion, it will get neutralized by the hydronium ion, and then you will get more hydronium ion by moving the reaction from left to right. So you're neutralizing most of the hydroxide ion, so you're not increasing the pH of the solution, right? Or it will increase or decrease very less. So this is how the buffer maintain the pH value. It doesn't change too much. Let's take an example of acetic acid and acetate ion buffer. This is your acetic acid, this is your acetate, a conjugate base, weak acid. This is a buffer component, right? And then the pH range of this buffer is from 3.8 to 5.8. So if you add any acid, a small amount of acid or base, the pH value might fluctuate, but it's not that much. So let's take again the same two example. If I add more hydronium ion into this buffer system, what's going to happen? Then the acetate ion is going to combine with the extra hydronium ion, and the reaction will move to the product reactant side. Means you're going to make more acetic acid, weak acid. So there is no effect of adding more acid onto the buffer system. If there was no buffer, if you add more acid, the pH value should go down and the solution become more and more acidic. But because of this reaction in the buffer system, the extra acid that you're gonna put in there is going to neutralize by the conjugate base, and the pH value won't decrease further. Let's take the same example again. If I remove the hydronium ion from here, if I'm removing the hydronium ion, that means you don't have any extra hydronium over here. The reaction will think, okay, we don't have more hydronium ion on the product side. The reaction will move to the product side to balance the concentration of the hydronium ion, because if you're removing the hydronium ion, is same as you are putting a hydroxide ion, right? You can say remove of hydronium ion is same effect like adding hydroxide ion, right? So if you add hydroxide ion or you remove hydronium ion, same thing. The reaction will move to the product side, and then you will maintain the pH of the solution. Let's take one more example of the buffer that is present in our blood, right? Carbonic acid and hydrogen carbonate buffer. So this your carbonic acid, when you dissolve in water, is a weak acid, is going to convert into a conjugate base, hydrogen carbonate plus hydronium ion. So this is your weak acid, this is your conjugate base, so this is your buffer system, right? This buffer system, so how you gonna make, so this is the way the buffer system of carbonic acid and hydrogen carbonate works in our blood, right? You can also make a carbonic acid in our blood by other mechanism, which we can see over here. If you have carbon dioxide in your blood, if it dissolve in water, you will have a combination reaction to make carbonic acid, right? So this is your weak acid, and if the H2CO3 is also going to convert into water and carbon dioxide through a process called decomposition reaction. So the reaction is going back and forth, right? So you can make a carbonic acid in blood by carbon dioxide too. So now let's see what's the central role of this carbonic acid. How does this buffer system work in our body? So what's the central role of carbonic acid? So we can know the carbonic acid, if the blood has the carbonic acid react with water, can produce hydronium ion and conjugate base, hydrogen carbonate ion. So this is your weak acid, And you can also produce in our blood. How we can get this carbonic acid in our blood before it can act as a buffer system? You can get carbonic acid in the blood by reacting carbon dioxide and water. And from where you're going to get the carbon dioxide? From the respiration, right? So when they react, they form carbonic acid. So carbonic acid is the center point, right, which is in between carbon dioxide and water reaction, and between conjugate base and hydronium ion concentration. So let's try to understand how does this mechanism work. So let's try to do how this buffer system work, right? If I put more as hydronium ion into the system, if I putting more hydronium ion, that means the extra of the hydronium ion that we are putting is going to react with the conjugate base, and then the reaction will go on the left side to make more carbonic acid. And if you have more carbonic acid present in the blood, then this reaction will go furthermore into the second reaction, which we call as decomposition reaction. The reaction will go towards the left side, means you are producing more carbon dioxide in the blood, right? So how does the body help? So body helps by removing most of the carbon dioxide from the body, or else you will have a lot of concentration of carbon dioxide in our body. So the lungs normally exhale carbon dioxide from the body, right? If we add more acid. So this is how the reaction is going. So carbonic acid is as a center point. For the same reaction, if I add more hydroxide ion, if you are adding more hydroxide ion, means you are decreasing the concentration of the hydronium ion. Why? Because hydroxide ion react with the hydronium ion and convert into water. So you will have less amount of hydronium ion on the product side. If you have less amount of the hydronium ion, the carbonic acid buffer system will move the reaction to the right hand side, right? Once the reaction moves to the right hand side, then this other reaction of carbon dioxide water carbonic acid reaction is also going to move on the right hand side, because most of the carbonic acid is converting into a hydronium ion. And then for the first reaction, the reaction will think we don't have enough carbonic acid, so carbon dioxide and water will react more and produce more carbonic acid. And if the reaction moves towards the carbonic acid, that means the concentration of the carbon dioxide in the blood will decrease, because most of them is going to use with water to make carbonic acid. That means the lungs will exhale less carbon dioxide, because most of the carbon dioxide being used in this reaction to make carbonic acid, and this carbonic acid can act as a buffer. So this is how all the reactions, both these reactions are connected, and this is the central role of carbonic acid in our blood. So yeah, so try to read this from the textbook too, and then try to understand the concept, whatever we discussed over here. Practice couple of problem on this from the textbook. And yeah, I think that should be it from this chapter, and then I'll see you on the next chapter on the next video. Bye.